Good morning, everyone. I'm Sarita Swanepoel, and in this video, we are going to have a short discussion on applications of maths in physics and specifically to electric circuits. Now, if you look at this question, we're looking at November 2018, first one. The learners perform an experiment to determine the EMF and the internal resistance, right, of a battery and using the circuit below. Now remember that word battery, that's the word we use for all the cells combined. So one cell over there will be represented by that long and that short line, but together they are called a battery. Right, now they tell you the learners use the recorded readings of current and resistance. Now, why does the current change? Because they've got a rheostat in there, right? And the rheostat is going to change the resistance, and that will change the current. And now they use the readings of current and resistance together with an equation given like that to obtain the graph below. Now, where does that one come from? Now, when I look at this graph, you will see the graph is a straight line and it is not through the origin, right? And the moment I have a graph like that, I'm going to try to write an equation in the form of y equals mx plus c, right? Here you will remember m refers to the gradient of that line and c is the y-intercept. So what do I need to do? I need to have resistance in the y position, and I need to have 1 over current in that x position, and then whatever is necessary to make a true equation. Now let's start with something that we know is right, and that is the EMF is equal to I times R plus small r. The EMF is all the energy given by the cell to every 1 coulomb of charge traveling through that circuit, and the small r is now the internal resistance, and the big R is the resistance of this whole external circuit, which is just the rheostat in this case. So that's the equation, and now I want to rewrite that to get it into that form. Now first off, I need 1 over I, so I'm going to divide by I on both sides, and I end up with my EMF divided by current is equal to R plus R, and then I want to write it with R in front so I can have my y-axis there. So R will be equal to EMF over I minus R, or you can rewrite it to see it better. It might be EMF times 1 over I minus R. And the moment that you do that, now we've got that in the y equals mx plus c form. And you can immediately see the gradient of that line will be the EMF. So wherever you work out the gradient of that line, anywhere that you work out the gradient of that line, you will find that will be the EMF. And the y-intercept over there is going to be negative R. At 9.1, they ask us which variable has to be kept constant in the experiment. Now, when you are doing this, there's two things that I'm going to keep constant. The first thing is, since I'm using the same cell, and you have to use the same cell, you will have the same EMF and the same internal resistance. And the other thing that you have to keep constant here is the temperature. If you change the temperature, then the resistance will change and everything will change. So what we usually do is you change the rheostat, you set this rheostat to a different resistance, then close the circuit, take the reading and open it. You don't leave the switch closed for long, because then everything would be heating up and then the resistance will change. So we are definitely going to keep temperature constant. Right, then refer to the graph. Write down the value of the internal resistance. Now we already know the internal resistance is going to be negative, that one. Then we are just counting the blocks to know how many is representing 1. Now there's 10 blocks over there, so every 2 blocks is representing 1, and then I end up with minus 3 over there. Right, so that tells me that the internal resistance is going to be, well, I've already 3 ohm over there, but I have to be careful. What I've got there is they're asking the cell, and what I actually have, I've worked with the whole battery. So that 3 ohm is actually for the whole battery. And if I have 2 cells in series, that will mean that is 1,5 ohm for every cell. Next up, 9.2.2, calculate the EMF of the battery. Now, what do I know? From my equation, I know the gradient of that line is going to be the EMF. So I will calculate that EMF by calculating the gradient of that line. So it must be change in y-axis divided by change in x-axis. We need to choose 2 data points on this line. Now, obviously, I've already have that one, so that's easy. And then let's just choose that one, which is also easy because that ends up being 7,5 over there. And we know it's 1,5 over there. And we can use that one where we already know the data. So change in y-axis, that will be 7.5 minus 3, and divided by change in the x-axis, final x value 1.5, original x value 0, and you end up with 7,00 volts. And remember, you have to put the 00 there. You need a minimum of 2 after the comma. Next, we're going to look at question 8 of that same question paper, and we're only looking at a small part of that question. They tell you the battery in the circuit, so once again 2 cells, battery in the circuit, has a total EMF of 12 volts EMF. That means, now if you think about the definition of EMF, even F is just the potential difference, so it is how much energy is provided to 1 coulomb of charge, right? How much energy is provided to 1 coulomb of charge that travels through the circuit. So the EMF is what the cell gives to this charges. The 0.5, that is my internal resistance, and that means there's voltage lost inside, right? We call it the internal or the lost volts, right? Now, if you think about a cell, small thing with chemicals inside, the chemicals are doing a chemical reaction that is providing that energy to 1 coulomb of charge traveling through the circuit. But to travel through the circuit means you have to travel through that battery, and that battery with chemicals have got a resistance of 0,5. You will use energy to travel through that. So there will be electrical energy converted to heat when the charges travel through there. So now when they ask us the question, they tell us switch S is now closed. How does this change affect the reading on the voltmeter? Now let's look at that voltmeter. That voltmeter, what does it read? It does not read the EMF at the moment. When will it read the EMF? When the switch, if there was a switch over here and that switch was open and I opened that switch, it would have meant no current flowing. And if there's no current flowing, then this voltmeter just read the EMF. But the moment that there's current flowing in the circuit, between that spot where I've connected my voltmeter and there where I've connected the voltmeter again, what happened to the charges? They receive a 12 volt EMF, but in that same cell, they also lose some of that 12, right? The lost volts or the internal volts are lost and they come out with less. So this voltmeter actually measures what's available for the external load over here to use. So now they tell you that this one is closed. Now before it was closed, charges could only travel through R there at the bottom, but now over there the circuit becomes branched, so now we've got 2 in parallel. So the moment that they close that, what they actually do is they add a resistor in parallel. And when you add a resistor in parallel, that immediately tells you the resistance of this whole circuit, of this part and therefore of the whole circuit, is going to decrease. Adding something in parallel is always making the resistance less, right? Now remember in the exam not to write arrows. You have to write it out, but I am allowed to write arrows. So moving on. Now I've talked about the resistance. Now let's talk about the current. What's going to happen to the current in the circuit? Now, if the circuit gets less difficult to move through, you will have a bigger current. But we have to have reasons for that. So let's start by saying, since I've got the same cell, I've got the same EMF and I've got the same internal resistance. That stayed constant. And if you look at EMF equals IR plus R, we now know that one is constant and that one is constant. And what happened to our resistance of outside the circuit has got a lower resistance, right? And if the resistance is lower, then obviously the current will be bigger. Now, we have talked about, and that would have been the ammeter reading would have been bigger, but that wasn't asked. What they're asking us is that voltmeter. Now, if I want to talk about the volts that's available for external, that voltmeter reading, I first have to consider what is happening internally, what is lost. Now, when the current increases, I want to know what's happening to the internal volts. Is it using less or using more energy in there? Now, for this, I will say V equals I times R, but if it's internal voltage, it's going to be internal resistance. And what do I know about internal resistance? That internal resistance is constant. Remember, I changed things outside. I didn't change the cell. So that R is a constant. And in the previous line, we just said the current is going to be bigger than before. And that immediately tells me more energy will be used up by the charges traveling through that battery. And then we want to talk about what's available outside. Now, obviously, if you have more lost inside, used up inside, then we will have less for the outer circuit. Because if you think about this, the EMF is constant. And if you look at the EMF is the voltage that's used internally and externally, right? It's the lost and the load. And this one is going to stay constant. And we've just now worked out that the internal voltage will be more. More will be used up inside. So to get the same answer, the external voltage will be less. And that is the answer to my question. So it will decrease. And for the 4 marks, you have to say everything. So that one is going to decrease. So 4 marks, if we think about this, the first mark will be for you to say that the total resistance is decreasing. The next mark is because you tell them that the current is now increasing and you have to give a reason as well. Third mark is because you've discussed the internal volts, and that's always doing the same as the current. If you've got a bigger current moving through there, then it's taking more energy to move them through per unit charge. And if you are using more, then the voltage outside or available for outside will be less. So there's the 4th mark. So guys, this is a very standard type of question. They change something and they're asking you what's happening to the voltage over the cell. Right. Now just be careful. Sometimes they put that voltmeter somewhere else. But for the standard type of question where they ask you what's happening to that voltmeter over the cell, you will always refer to the resistance of the outside circuit and see how that is changing. Then telling them that the current is going to do the opposite thing. And the reason must be added for you to be able to get the mark. And then telling them what's happening to the lost, the internal volts, because the external ones will be doing the opposite, because together they need to have a constant EMF given to us. Right, guys? So you can go and practice this. So go and find the questions in the old exam question papers that require you to do this, considering if I change this, what's happening to that. Right. Now, I hope you've enjoyed maths and physics, because there's a lot of questions where you need this manipulation of equations, or like we've done in the previous one, writing equations for lines that are not going, straight lines that are not going through the origin.